In basic crystal field theory, approaching ligands split the d orbitals of a central transition metal into distinct lower and upper energy levels. Mathematically, a system with a single energy gap implies a single possible electron transition. Under this model, a given metal complex should produce exactly one absorption band. This chart shows an actual UV-Vis absorption spectrum for a complex like hexa-aqua vanadium-3. Instead of a single spike, we observe 3 distinct prominent absorption peaks. If the base orbitals only have one energy gap, where are these extra transitions coming from? The standard model falls short because it treats electrons as entirely independent entities. It ignores the repulsive forces and interactions that occur when multiple electrons occupy the same outer shell. To accurately map real spectra, we cannot look at the transitions of isolated single electrons. We have to analyze the energetic state of the entire atom. When an atom has multiple d electrons, their individual spin and orbital angular momenta couple together. This coupling, known as Russell-Saunders coupling, organizes the electrons into distinct energetic groupings called microstates. These are categorized by lettered term symbols, primarily S, P, D, and F. In the presence of a ligand field, these entire coupled atomic states split into new energetic levels. Tracking how these complex multi-electron states split across different molecular geometries requires a specialized map. The Orgel diagram provides that map. It acts as a translation layer, taking abstract atomic states and showing exactly how they will generate predictable spectral peaks. We begin building this map with the simplest group of electron configurations, those that share a d ground state. This includes atoms with 1, 4, 6, or 9 d electrons. This graph charts energy on the vertical axis against ligand field strength on the horizontal axis. We place our starting d ground state squarely in the center, representing an environment with 0 ligand field. For a D1 metal in an octahedral field, moving to the right of the diagram shows how the D state splits into a lower T2G level and an upper EG level. This singular split yields exactly one possible electron transition, missing exactly one electron. We can treat that single missing space as a positive hole, moving through a background of negative charge. Exciting a single electron upward in a D9 system is physically and mathematically equivalent to this positive hole dropping down to a lower energy level. Because the hole has an inverted charge relative to an electron, its energy splitting pattern inside the ligand field is perfectly inverted as well. We can map this inverted D9 octahedral relationship on the left side of our diagram. The split mirrors the right side, but the positions are flipped. EG is now the lower state, and T2G is the upper state. By treating missing electrons as positive holes, a single diagram can predict the energy states for heavily populated electron shells just as easily as nearly empty ones.
The diagram relies on a second master symmetry, the geometric relationship between molecular shapes. A metal complex with a tetrahedral geometry naturally creates the exact inverse splitting pattern of an octahedral complex. Because of this geometric inversion, we assign the D1 tetrahedral configuration to the left side of our chart, placing it exactly alongside the D9 octahedral state. We then map the D9 tetrahedral configuration to the right side. All 4 starting D-state configurations across both geometries are now consolidated onto a single continuous axis. This same logic scales up to the remaining weak field configurations, atoms with 2, 3, 7, or 8 d electrons, which share an F ground state. This diagram shows the master map for those F states. Because these atomic states contain more angular momentum, they split into 3 distinct branches, T1G, T2G, and A2G. Notice the distinct upward curve of the highest state. Energy levels that share the same symmetry, like the excited P state and the upper F state, repel each other, bending their trajectory as ligand strength increases. Between the D and F diagrams, we possess the mathematical maps needed to predict multi-peak spectra across every weak field configuration. We can apply the F-Orgel diagram directly to experimental data by looking at a hexaamine nickel-2 complex. To read the map, we define our parameters. Nickel-2 is a D8 metal, and its 6 ammonia ligands form an octahedral geometry. Referencing the diagram, an octahedral D8 configuration dictates looking exclusively at the left-hand quadrant. We identify the lowest energy line, the 3A2G state, as our baseline. From that ground state, the geometry permits exactly 3 spin-allowed transitions up to higher energy curves. Placing this nickel complex in a spectrometer, the data yields exactly 3 distinct absorption peaks. The Orgel diagram correctly diagnoses the exact number of energetic states hidden within the complex. Orgel diagrams successfully predict the number of absorption peaks, but consistently overestimate the specific energy values observed experimentally. The discrepancy arises from the model's base assumption. Orgel diagrams are constructed assuming the bonds between the metal and the ligands are purely ionic. In practice, pure ionic bonds rarely exist. The central metal and the surrounding ligands exhibit some degree of covalency, meaning they share electron density. When electrons are shared across a covalent bond, the localized electron cloud expands outward, diffusing its density over a wider physical area. This expansion is known as the Nephilauxetic effect. Because the electrons are spread over a larger space, the forces of interelectronic repulsion are significantly reduced. With weaker repulsion forces pushing the electrons apart, the transitions require less total energy. This shifts the real-world absorption peaks to slightly lower frequencies than a purely ionic model calculates. Orgel diagrams provide the rigid architectural grid for mapping electron behavior, but accurately predicting chemical reality requires adjusting that grid to account for the covalent nature of the bonds themselves.